Hey, welcome. So think about this for a second. You are interacting with dozens, maybe hundreds of pieces of software right now. I mean, from the app on your phone to the system running the entire power grid. But have you ever really stopped to think about how all this stuff gets built? Well, today we are going to pull back the curtain on the huge field that really shapes our modern world, software engineering. Because, let's be honest, in a world that completely runs on code, you really got to understand how it's built right.
And that brings us to this central puzzle, right? We rely on these incredibly advanced software systems for everything, commerce, medicine, you name it. And yet, actually building that software is notoriously, ridiculously difficult. You hear about it all the time. Projects run way over budget, they get delivered late, or they just fail completely. So why is something so essential to our lives so incredibly hard to get right?
To answer that question, we first have to get our heads around the core problem that software engineering was actually created to solve. So in this first section, we're going to dig into the hidden costs and the crazy complexities of software development.
Okay, so this chart right here, it just flips a huge assumption completely on its head. We all tend to think that building the software, the initial creation, is the big expensive part. But for most systems that are going to be around for years, the real cost comes way later. The maintenance, the constant updates, the evolution. That can end up being several times the initial development cost. It really tells you that software isn't just a product you buy off a shelf. It's a long-term commitment.
So why do so many of these projects just go completely off the rails? Well, it's usually a perfect storm of these three things. First, the complexity is just always increasing. As soon as we figure out how to build something, we immediately want to build something way bigger and way better. Then you pair that with this constant demand to deliver everything faster. But honestly, the biggest reason for failure is that a lot of teams just skip the engineering part. They just start coding. And that's like trying to build a skyscraper without a single blueprint. It's a recipe for an expensive, unreliable disaster.
Right, so faced with these skyrocketing costs and this massive complexity, a more structured approach was desperately needed. And that brings us to our second section. What is software engineering as a formal discipline designed specifically to tame all of this chaos?
Let's just look at the formal definition here, because the words really matter. It's not just about coding. It is an engineering discipline, and that is absolutely crucial. It means you're using the right theories and methods to solve problems, but you're also thinking about things like budgets and organizational limits. And notice it says all aspects of production. That means from the very first spark of an idea all the way to keeping that system running years and years down the line.
Now, this is a question that comes up all the time. You might be thinking, okay, you're building software, you're using a computer, so isn't this all just computer science? And you know what? The answer is a really clear no, and the difference between them is super important.
Here's probably the simplest way to think about it. Computer science is the theory. It's the fundamentals. It's like understanding the physics of steel and glass. Software engineering, on the other hand, is the discipline that uses that science to actually design and build a reliable 100-story skyscraper. It's all about the practical stuff, building something huge, on time, on budget, with a big team that isn't going to fall down the first time the wind blows. One is the science of what's possible. The other is the discipline of making it real.
So how does this whole discipline actually work in practice? Well, it basically breaks the entire process down into 4 key activities that all flow into each other. It all kicks off with specification, and that's where you define exactly what the software is supposed to do. Then comes development. This is the part you probably think of, the actual design and coding. But you are not done yet. Next is validation, which is where you rigorously test and check, did we actually build what the customer asked for? And finally, because the world is always changing, there's evolution. That's modifying and improving the software for years to come.
You see, following this process isn't just about trying to avoid failure. It's about actively creating success. So let's move on and take a look at what the blueprint for good software actually looks like when you're using these principles. According to this discipline, good software isn't just about having a bunch of cool features. It has to deliver on 4 essential promises. It's got to be maintainable, so you can actually update it later without breaking everything. It needs to have dependability and security, so we can actually trust it with our data and, our safety. It has to be efficient, so it doesn't waste our time or hog all our computing power. And finally, it has to be acceptable, which just means that real people can understand it, use it, and feel like it actually fits their needs.
Now let's just zero in on dependability for a second, because this is where the stakes get incredibly high. Dependable software is software that won't cause physical or economic harm if something goes wrong. Think about a safety-critical system, like a personal insulin pump. A failure there isn't just an oops or an inconvenience,
It could literally lead to a coma or even death, and this is exactly why a disciplined engineering approach is absolutely non-negotiable. And that brings us to a really crucial point. When you're building systems that have life or death consequences, well, the job involves a whole lot more than just technical skill. So our next section is going to look at the professional and ethical responsibilities that come with being a software engineer. I mean, just look at this quote from the rationale behind the official Code of Ethics. It says it all, doesn't it? Software engineers have significant opportunities to do good or cause harm. That kind of power demands a real, professional commitment to always using those skills for good.
This responsibility gets formalized in a code of ethics, and it really boils down to 4 key promises. A promise of confidentiality. You have to protect your client's sensitive information. A promise of competence. Be honest about what you can and can't do, and don't take on work you can't do well. Then there's a respect for intellectual property. And finally, a hard line against computer misuse. A duty to never ever use your skills to cause harm, like writing viruses or malicious code.
To make this really concrete, think about a healthcare system. Let's call it mental care. A core ethical duty there is confidentiality. Period. Patient information about mental health is incredibly sensitive. Protecting that data isn't just a feature you can check off a list. It is a fundamental professional obligation. All right, so we've covered the problem, the discipline that solves it, the goals of that discipline, and the ethics that guide it. So for our final section, let's tie this all together and answer the big question. Why does any of this matter?
And at the end of the day, here's why it all matters. We live in a society that is completely dependent on massive, complex software systems. Software engineering is the framework that lets us build them in a way that's reliable, trustworthy, and affordable. It's the difference between throwing together a rickety shack of code and actually engineering a skyscraper that can withstand an earthquake. It's the discipline that brings order to the chaos.
And that kind of leaves us with one final thought to chew on. As software gets more and more tangled up with every single aspect of our lives, from our health to our government to how we connect with each other, the principles of software engineering, they aren't just technical guidelines anymore. They're essential for a society that actually works. So the real question for all of us is this. In a world that is truly built on code, how do we make sure that code is built for the public good?